let's keep going with the next 4 examples where we are still trying to determine whether the series converges absolutely or conditionally or diverges. The first thing we need to do is find the absolute value of a sub n. Notice this is an alternating series. Why is it an alternating series? Because we have -1 raised to the n, so I know that this is an alternating series. Therefore, the absolute value of a sub n is just going to get rid of that -1 to the n, because again, when you multiply something by -1 to the n, you're alternating between a -1 and a +1. So its absolute value would be just 1 times n over 3n plus 2, or just n over 3n plus 2, because you really don't need the times 1. So n is still going to be n, 3n plus 2 is still going to be 3n plus 2, but the absolute value of this guy here is that 1. So now that we have the absolute value of a sub n, we have to determine, does this diverge or does this converge? Well, n over 3n plus 2 is not a known series. It's not a p series, it's not geometric, and it's not telescoping. So the next thing we always try is the nth term test. So let's figure out if this diverges by the nth term test. What is the limit as n goes to infinity of n over 3n plus 2? Well, currently, this would just be infinity over infinity. If we look at those leading terms, n over 3n, we would get the limit as n goes to infinity, reducing here, 1 over 3, because n over 3n, the n's would cancel, and we'd be left with 1 over 3. Well, what's the limit as n goes to infinity of 1/3? Well, that would equal 1/3. Well, 1/3 does not equal 0, therefore by the nth term test, the series diverges. Since the series diverged, now we try the alternating series test. The alternating series test says the first thing you do is do the limit as n goes to infinity of a sub n. What is the limit as n goes to infinity of n over 3n plus 2? Well, we just figured that out. That is 1/3. Well, 1/3 again doesn't equal 0. Remember, the conditions for the alternating series test said that the limit as n goes to infinity of a sub n had to be 0. That was not met. Recall what this note said. If the limit as n goes to infinity of a sub n doesn't equal 0, then this series diverges by the nth term test. Since the conditions were not met, we know that this series diverges by the nth term test. Number 3, the sum from n equal 1 to infinity of -1 to the n plus 1 over 5 to the n plus 7. The first thing we do is find the absolute value, because we notice that this guy here is an alternating series. Well, the absolute value of a sub n is going to be, well, the absolute value of that is just going to be a 1 over the denominator, which is 5 to the n plus 7. Well, that is not a known series, so we could try the nth term test, but the problem here with the nth term test is that we'd have the limit as n goes to infinity of 1 over 5 to the n plus 7, and that's just going to be 1 over infinity, which is equal to 0, which means my nth term test fails. So I can't use the nth term test. Well, now we have to find a different test to use to figure out if this converges or diverges. Our options now are the integral test, the direct comparison test, or the limit comparison test. I typically don't use the integral test unless I have to, because for the integral test, I have to show that something is continuous, positive, and decreasing, and sometimes that takes a lot of steps. Instead, I will try the limit comparison test and the direct comparison test first and save the integral test for last. Please note that when you use the integral test, your series has to be something you can integrate. For example, we could not integrate this series. So if we're going to do either direct comparison or limit comparison, we need to figure out what to compare this to, so let's look at those leading terms to know what to compare this to. Well, what is the leading term of the numerator? Well, the leading term of the numerator is 1. What's the leading term of the denominator? Well, that's 5 to the n. Well, this looks geometric, so we are going to compare it to the sum from n equals 0 to infinity of 1/5 to the n, because 1 over 5 to the n is the same as 1/5 to the n. What do we know about this? Well, the absolute value of r is equal to 1/5, and that's a number that is less than 1, therefore we know that this will converge. So we can either do a direct comparison or a limit comparison. Let's go ahead and just do a direct comparison. If we're doing the direct comparison test and this converges, we know that it has to be the bigger series. If it has to be the bigger series and we're looking at 0 less than a sub n less than or equal to b sub n, that means that this guy here is my b sub n, and then this given here would be my a sub n. So I say 1 over 5 to the n plus 7. Is that less than or equal to? Well, instead of writing it as 1/5 to the n, I can write it as 1 over 5 to the n. If I cross multiply, I get 5 to the n. Is that less than or equal to 5 to the n plus 7? Yes, that's true. Therefore, by the direct comparison test, our series converges, but remember, we took its absolute value to converge, so we're going to say that our series converges absolutely. And since our series converged absolutely, we're done. We do not try the alternating series test. If we go back to those directions that I had at first, remember it says first find the absolute value of a sub n and determine if that converges or diverges. If the absolute value of a sub n converges, your series converges absolutely and you're all done. Since with example 3, our series converged when we took its absolute value, it converges absolutely. Let's try number 4, the sum from n equal 1 to infinity of the sine of 2n minus 1 times pi over 2 all over n squared. Well, this doesn't look like the alternating series that we're used to looking at, because all the ones we've seen before have either a negative 1 to the n or a negative 1 to the n plus 1. But this part here is actually the alternating piece. Why? Well, first thing, 2n minus 1 is the formula for an odd number. So 2n minus 1 is going to be a formula for an odd number. Let's think about it. If n is equal to 1, we'd have 2 minus 1, or 1. When n is equal to 2, we'd have 4 minus 1, which is 3. When n is equal to 3, we'd have 6 minus 1, which is 5. We'll do just one more. When n is equal to 4, we'd have 8 minus 1, which is 7. So this guy here gives me odd numbers. Well, if you look at what's going on in this piece here, it says 2n minus 1 times pi over 2. Now if I take 1 and I multiply it by pi over 2, I get pi over 2. If I take 3 and I multiply it by pi over 2, I get 3 pi over 2. 5 times pi over 2 is 5 pi over 2. And then 7 times pi over 2 would be 7 pi over 2. Well, this formula is saying, hey, once you figure out what this guy here is, then take the sine of it. So what would the sine of pi over 2 be? Well, that's 1. What about the sine of 3 pi over 2? Well, that's negative 1. What about the sine of 5 pi over 2? Positive 1. The sine of 7 pi over 2? Negative 1. Notice that we are alternating between positive 1 and negative 1. Because of that, this portion here is what's making us an alternating series. If we have to find the absolute value of a sub n, again, this portion up here alternates between positive and negative 1, so when we take that absolute value, all we're left with in that numerator is a 1. The denominator stays as n squared. So the absolute value of a sub n here is 1 over n squared. Now what we need to do is we need to figure out, does this converge or diverge? Well, this is a known series. It's a p series. Here p is equal to 2. Since 2 is greater than 1, we know that we converge. Since we converge, and we took the absolute value of this series, we know that this series converges absolutely. So with alternating series, You're either going to converge absolutely, that happens if the absolute value of a sub n converges, converge conditionally, that happens if the absolute value of a sub n diverges, and then you try that alternating series test and your conditions are met. Or your series diverges, and that happens if the absolute value of a sub n diverges and you do not meet the conditions of the alternating series test. Okay, let's look at our last one, number 5, the sum from n equal 1 to infinity of negative 1 to the n over the square root of n squared plus 1. Again, we know that this is an alternating series because the numerator is a negative 1 to the n. We start by taking the absolute value. Well, the absolute value of a sub n is going to be 1 over the square root of n squared plus 1. Well, that is not a known series, so we have to figure out how to determine if that converges or diverges. Well, if we were to do the nth term test, we know that it's going to be the limit as n goes to infinity of 1 over the square root of n squared plus 1, and that's just going to be 0, so this test fails. We have to try a different approach to determine if this converges or diverges. Again, I typically try to do direct comparison or limit comparison test. So let's determine what we should compare it to. What is the leading term of the numerator? 1. What is the leading term of the denominator? The square root of n squared. And the square root of n squared is just a 1 over n. So we're going to compare this to the sum from n equal 1 to infinity of 1 over n. That is a p series. There your p is equal to 1, therefore you know you are going to diverge. What you need to do now is decide whether you're going to do the limit comparison test or the direct comparison test. Since we did direct comparison test on example 3, let's go ahead and just try the limit comparison test. Now the limit comparison test says to take the limit as n goes to infinity of given, well the given is this guy, our 1 over the square root of n squared plus 1 times the reciprocal of our known, or divided by our known, which is always going to be times the reciprocal of our known. Well, the reciprocal of a 1 over n is n over 1. If we multiply, we have the limit as n goes to infinity of n over the square root of n squared plus 1. Well, that's currently just infinity over infinity, so we could use L'Hopital's rule, or we can again just look at those leading terms. I'm going to have an n over the square root of n squared. Well, I know that the square root of n squared cleans up to just be n, so this is just n over n. Well, what's the limit as n goes to infinity of n over n? Well, really that's just the limit as n goes to infinity of 1, which is 1. 1 is a finite positive number. Therefore, by that limit comparison test, we know that our series diverges. Since the absolute value of our series diverged, now we try the alternating series test. Again, when we're dealing with alternating series, you first take the absolute value of the series and determine if that series converges or diverges. If it converges, we're done, we converge absolutely. If it diverges, then we try that alternating series test. The alternating series test has two conditions. Condition number 1, the limit as n goes to infinity of a sub n, which we know is at 1 over the square root of n squared plus 1, has to equal 0. Well, this does because it would be a 1 over infinity, so the first condition is met. Condition number 2 is that it must be decreasing, so a sub n plus 1 has to be less than or equal to a sub n. So a sub n plus 1 would be 1 over, and instead of n I'd write the square root of n plus 1 squared plus 1. Is that less than or equal to 1 over the square root of n squared plus 1? Well, let's say I'm not sure. We know that we can cross multiply. If we cross multiply, we'd end up with the square root of n squared plus 1. Is that less than or equal to the square root of n plus 1 squared plus 1? Let's say we can't tell here. If we raise both sides to that second power, we'd have n squared plus 1 less than or equal to n plus 1 squared plus 1. If we still couldn't realize it at this point, we know that at least our 1's would cancel from both sides. And now we're just really looking at n squared less than or equal to n plus 1 squared. Is this true? Yes, n squared is going to be smaller than n plus 1 squared. Therefore, since our conditions were met, by the alternating series test, our series converges conditionally. And the reason it converges conditionally is that the only reason it converges is because it's alternating. If it wasn't alternating, it would diverge.